Okay, so in this video lesson, we will construct explicit and recursive equations for linear and exponential functions. And as we talked earlier, a linear function is represented by an arithmetic sequence, and an exponential function we sort of notice is in geometric sequences. So you should have this sheet in front of you. And let's take a moment first to look at our graph, or rather our table. So as I move down, as I go from my zero term or my x value of 0, and I move down through my x's and I move down here, I notice that it is increasing. So how is it increasing? Well, I can go from 1 to 4 by adding 3, but I can't go from 4 to 16 by adding 3. That wouldn't work both ways. So I notice that I am multiplying by 4 each time. Right? 1 times 4 is 4, 4 times 4 is 16, and that works for the entire set of values. So being that I'm multiplying by 4, my 4 represents my common ratio. So I'm going to write that up here. Common ratio is 4. And also it tells me that this has to be a geometric sequence, right? Because geometric means that I'm multiplying by a common or a constant number, and my constant number here is going to be 4. So let me go ahead and graph that. You notice I sort of put these intervals 0, 1, 2, 3, 4, 5, 6, and 5 to, I counted by 5s going up on my y-axis. So at 0, it looks like I have 1, right? And my 1 is going to be somewhere in between. A little bit more than that maybe, but somewhere right there. At 4, or rather at 1, I have 4. At 2, I have 16. At 3, let's see, 64. So I'm already off my graph. So 64 would be somewhere around here maybe. And I'm going to assume that this is a continuous function. So I'm just going to go ahead and connect my dots, or connect the dots here, right? So it looks something like this. And as we mentioned before, if my graph obviously is not linear, it does not make a straight line, but it increases exponentially. So this represents an exponential function. All right. So now that we know that, let's go ahead and look at our table here, and I'll just put this again, or our questions. So it looks something like this, and of course that's not at all what it looks like, but we have an idea. All right, so is this arithmetic or geometric, or neither? Well, we just said that it is a geometric, and we also said that it is exponential, right? It increases in an exponential way. Okay, so let's also make another assumption here. Let's assume, and in fact, if we are assuming that, oh no, let's assume it starts at 0 as our starting point, and that it goes on infinitely. So our range would be, again, if I write that as a compound inequality or as an inequality, I would start with 0. It's our smallest value, is less than or equal to x. But there is no ending, because as you look at the graph just continues infinitely, right? So I could do something like this, but why? So that's really not necessary. Then let's look at the range, right? The range represents our y values. So again, it would be 0 is less than or equal to y, because again, the range is here, and it goes up and up and up past the end of my screen here, and the x is going to continue to go over. So this would be the range and domain. Now let's assume that I didn't have, had a closed point here at 5, and 1,204 was the highest it went as the height. It would look something like this. 5, right? We just looked at our table, and our y would be similar, in that our ending point would be 1,024. Okay? So that arrow makes all the difference in writing the domain and the range. Okay, So what is the rate of change? Well, the rate of change is that it is increasing by 4 each time. It is increasing by 4, and it's increasing through multiplication. So we're multiplying by 4 each time. And we talked about the explicit and recursive. So the explicit is our starting point. Let's first list our starting point. Well, that starts at 1. Right? That's where we start. And our rate of change, well, we multiply that by 4. And I'm going to raise that to the x power. And the reason why I raise it to the x power instead of x minus 1 is because notice here it starts at 0, right? So if it started at 1, I would have to do x minus 1. And this is f sub x equals this. Now, I could also write I could write it let me leave it at that. And so let me also include this, that I start at my 0 term is 1. And again, my recursive, so that's where we have to just look at the previous term, and our previous term is represented by f sub n minus 1 times our common ratio, which is 4. All right, so I'm going to use my explicit formula to find f of 6. So let's see here. I'm going to do 1 times 4 raised to the 6th power. So if you have your calculator, you're going to do 1 times 4, which is 4, and 4 raised to the 6th power would give you 4,096. So that would be 4,096. All right. So now let's look at this one. How is it increasing from 1 to 2? Well, the y is increasing by adding 8. Okay, is that true? Plus that, yep. I add another 8 here. I add another 8, etc. So in this situation, I have a common difference. And my common difference is 8. So now I'm going to graph that, but right away I notice something. I notice that I don't have a y-intercept, or I don't have a starting point. So remember, when I'm graphing this, it's usually helpful. I could start here at 1 and then go to 30, right? I could do that. And I could do 2 and go to 38. And 3, 46. 4 would be 54. And 5 would be 62, somewhere around here, right? But I don't know where my y-intercept is. So let's write that, because we need that to do our explicit form, or explicit formula. So I want to figure out my 0 term. So I've been adding by 8 each time. So I'm going to subtract 8 here. So 30 minus 8, well, that would be 22. And so my y-intercept would be 0, 22. So where would that be? Right around here. And again, let's just say this is a discrete formula, or discrete function. So I'm not going to connect these. These are all separate points. So if we're going to answer these questions, well, we just noticed that if I'm adding by a constant, then that must be arithmetic, right? And we graphed our equation, right? We graphed our table here, and that looks very linear. So arithmetic is our linear functions. And domain. So if now that we said that this is a discrete function, so we want to list our domain as a set versus a compound inequality. And I'm also going to make an assumption here that it ends at 70 and it ends at 60. So I'm just going to list all those numbers for my x: 1, 2, 3, 4, 5, and 6. Because I said that that is all the numbers within that function. And my y, or my, let me make sure it's clear here, this is my h of x. H of x is going to be 30, 28, or sorry, 38, 46, 54, 62, and 70. So I made a list of those values, okay? So the rate of change, what's going on here? Well, I'm adding 3 or 8. My mind is gone. I'm adding 8 each time here. So the explicit formula for an arithmetic sequence, well, that is just like our linear equation, right? Y equals mx plus b, b being our starting point, m being our rate of change. And well, I know that my rate of change is I'm adding 8, so it's going to be a positive 8. So I have y equals 8x plus, what was my starting point? Well, that was 22. That was my 0, comma 22. So I'll put my 22 here. Okay, now the recursive, while we did not like that recursive at the start, it's not really helpful when we're solving equations, but it's pretty easy or to simply write, right? So I have my previous term plus my common difference, and my common difference here is 8. So let's use the explicit again to figure out what f of 8 is. And I say use the explicit because I would have to figure out the 7th term in order to use my recursive. And I don't know what the 7th term is. All right, so let's plug our values in. So we're trying to figure out 8. So I have 8 times my substitute 8 for x plus 22. All right, so here I'm gonna put it in my calculator. 8 times 8 plus 22 gives me 86. All right, 64 plus 22 is 86. All right, so hopefully this video is useful. We will be having a quiz on some of this information come Monday. So if you have questions, just shoot me an email or let me know on Remind. Talk to you soon. Bye.